In this video, we are talking about plane wave reflection at material interfaces on normal incidence. So what we mean by that is that we have two materials, one of which has epsilon1 and mu1 as material parameters, and another one that has epsilon2 and mu2 as material parameters. Let's color in material 2 because we can. We're going to draw an analogy from this problem to the problem that you're already familiar with about transmission lines and reflection at the load. So in this situation, the forward-going voltage and current waves already have a fixed relationship. They have this proportionality with the characteristic impedance. And a similar proportionality happens if you have a plane wave that's propagating in medium 1. Now it's time for me to sort of do an aside and talk about rays and wave fronts. So if I draw a plane wave like this, this is one way of representing a plane wave, and that is a ray representation. So it gives you the direction of propagation for plane wave number 1. We're going to call that the ray. And I've also, these are sort of a bonus, drawn the directions of the fields. I can do the same thing in medium 2. I can draw the wave vector in medium 2, which might have a different length. In this problem, it's not going to have a different direction, but they will in other problems. And similarly, the electric field vector and magnetic field vectors also might have different lengths or different directions. So that sort of a representation is a ray representation. We can also draw wave fronts, if we're going to draw a wavefront representation of these waves, it'll look more like this, where we have the planar wave fronts of wave number 1 impinging on this boundary, and then on the right-hand side we'll have the planar wave fronts of plane wave of the same plane wave in medium 2. I tend to prefer to draw things in the ray representation, but everybody's got their own way of doing it. So like I was saying about transmission lines. In transmission lines, your forward-going voltage and current waves can be compared to your incident plane wave. Right? And I'm going to rename H1 and E1 to HI and EI for incident. So EI is analogous to this forward-going voltage wave, and HI is analogous to this forward-going current wave. And as you might expect, they also have an impedance term that relates them. That's the intrinsic impedance of medium 1, because that's the medium that they're in. Now on a plane wave, when V plus and I plus arrive at this boundary that is the load, they have to do something in order to satisfy Ohm's law here with a different value of impedance, right? ZL is not equal to Z naught. And that's how the reflections arise. Reflections arise so that V total over I total is equal to ZL, and V plus plus V minus, this is the reflected wave, is equal to V total, and I plus minus I minus, because of the different directions of the current, is equal to I total. In exactly the same way, and I'm going to walk through and derive the whole thing, electric and magnetic fields, when they are propagating and being incident on this boundary, do exactly the same thing. So let's talk about that. I'm going to draw you a little equivalence table as we move along. So plane waves over here and transmission lines over here. For a transmission line, you have a forward-going voltage wave. That is the incident electric field in the plane wave problem. You also have a reflected voltage wave. That is the reflected electric field in the plane wave problem. You have a forward-going current. That's the incident magnetic field. You have a reflected current. That's the reflected magnetic field. You have a total current as a function of position. I would say that that counts as E1, so that's in medium 1. I'm going to say IZ and H1 are also kind of going to go right there. And then you have VL and IL, the voltage and current at the load, and that is going to be E2 and H2 at the interface. Impedances correspond to intrinsic impedances of the media. Propagation constants correspond to wave numbers. Reflection coefficients correspond to reflection coefficients. Oh yeah, there's going to be one of those. Standing wave ratios both exist in both problems. A lot of things are the same. So let's walk through and talk about how this problem works.